Hello everyone, it's my honor to be here today. The paper is In-Vehicle FlexRay Network Security based on Modified AES Encryption Algorithm, and I come from Yanbian University. This paper will divide it into main 5 parts. The first part is introduction. For a long time, in order to ensure the network security of the vehicle bus network, automobile manufacturers have unified the use of lean, CAN, and FlexRay buses to independently build the vehicle bus network. However, the development of vehicle bus networks faces many challenges: the network security, data management, and the network topology technology of the vehicle bus network traditionally lack security guidance and have strong arbitrariness and hardware dependence. In July 2015, two cybersecurity experts, Miller C. and Wallace C., hacked into the cars, so many people will pay attention on the security of cars. The second part is FlexRay Protocol. In this feature, we can see the frame of FlexRay data frame is divided into 3 parts: the start segment, the payload segment, and the end segment. We can see the payload length indicates the length of the payload of frame, and header CRC is used to check the redundancy of the initial segment and errors in transmission. The payload segment contains valid data to be transmitted. The trigger segment is composed of 3 bytes CRC check node. And the second part is the AES algorithm. In this paper, the picture we can see is the process of AES encryption and decryption. Each step of the decryption algorithm corresponds to the reverse operation of the encryption algorithm. The sequence of all encryption and decryption operations is precisely the opposite. The joint process of each step of the encryption algorithm, the decryption algorithm ensures the correctness of the algorithm. The key for each round of encryption and decryption is obtained from the seed key through a key expansion algorithm. And this paper proposed the modified AES algorithm. In order to further improve the encryption efficiency, and the column mixing change is to multiply the matrix after the previous transformation with a constant matrix, so that each element in the matrix is the weighted sum of all the elements in the original column of the elements. Among them, the multiplication is performed on the finite field GF field, and the modulo polynomial GX is required in the AES algorithm. The matrix can be expressed by expression 1. And the column mix of the ith column is in the state matrix can be expressed by the fraction 2. The inverse mix the transformation is expressed by matrix multiplication in fraction 3. And in this paper, in order to increase the speed of message encryption and reduce the number of multiplication, the above-mentioned metric is replaced with an optimized metric multiplication. Let G be a generator in the finite field. Then M, N, O, P are the orders of A, B, C, D, respectively. Then can be constructed as the following expression. The expressions file can be obtained through the calculations of the conventional metric, and since any elements in GF can be obtained by the power from GK of the generator G, all polynomials can be obtained in the form of the power of G. Then the metric M that satisfies the constraints is M. The fourth part is the experimental results. In order to verify the effectiveness of the modified max quantum AES encryption we proposed in this paper. The paper carried out 5,000 encryption and decryption experiments on 4 groups of FlexRay message data. Feature 6 is a time compression line chart obtained in MATLAB for encrypted FlexRay message data, and B shows the situation during decryption. We can see, compared with the original AES algorithm, the encryption speed of the modified AES algorithm is increased by about 26%, and the decryption speed is increased by 30%. It can be seen that the modified AES algorithm proposed in this paper reduces the time delay when encrypting and decrypting FlexRay messages. In order to further verify the effectiveness of the modified AES algorithm proposed in this paper on the vehicle FlexRay bus, this paper uses the CAPO languages to write the modified AES algorithm program. It conducts simulation verification through Canoe vehicle bus network development equipment. And in the feature, we can see new ECU TX and the new ECU RX are the sender and the receiver nodes of the FlexRay bus, respectively. In the right feature, we can see the message data, and there is no error. In this paper, 2 FlexRay hardware development boards are used in FlexRay transmitter and receiver nodes, and VN8970 is used as the FlexRay communication interface to realize the communication between Canoe and 2 FlexRay nodes. The structure of the hardware experiment environment is shown in the figure, and the actual hardware simulation environment is shown in the figure. In the last is the conclusion part. Aiming at the network security problem is of FlexRay bus. This paper innovatively proposes and modified the mixed column AES algorithm encryption scheme based on the analysis of the software and hardware, experimental simulation analysis results based on the Canoe and FlexRay development version. The modified AES encryption speed is about 26% higher than the traditional AES encryption algorithm, and the decryption speed increases by 30%. This scheme can effectively encrypt and improve the time-consuming problem of encryption and decryption of the original AES algorithm. The further improves the encryption and decryption speed and efficiency. At the same time, it makes up for the key problems of resource waste and time delay when encrypting and decrypting FlexRay message data, and lays a solid foundation for the network security technology of the onboard FlexRay bus network. The future work will contain about two parts. The first one is considering the robust of environment, and the second part is how to improve the algorithm performance.